Good morning, everyone. I'm pleased to welcome you to the second webinar organized by the EU-funded project Fuelphoria. My name is Piero Valmassoi, Project Manager at Greenovate Europe and also Communication Manager of the project. Fuelphoria is an EU-funded innovation action project coordinated by CERT, the Center for Research and Technology of Greece. And the project started in October 2023. And it works to establish a sustainable, competitive, and secure value chains from advanced biofuels and renewable fuels of non-biological origin. The project demonstration pilots are located at 4 sites in Belgium, Greece, and Spain. And they foresee the active involvement of all players along the value chains, from feedstock suppliers, technology providers, and end users. This will help to demonstrate that different types of feedstock, CO2, digestate, municipal biowaste, and others, can be converted into a series of renewable gas and liquid fuels suitable for transport and power production. The focus of today's webinar is, as you can see from my first slide, on the conversion pathways of sustainable feedstock for biofuel production that are performed across the 4 different Fuelphoria demo sites, with a distinction between catalytic and biological processes. In my next slide, you can see the detailed agenda of this webinar, and right after my short introduction, we will have a general overview of the project provided by our coordinator, Kostis Atsonios from CERT. And the next presentation will dig into the main topic of the webinar. And demo sites leader will present the main objective, current progress, preliminary insights from laboratory scale results, and we'll also showcase upcoming plans and challenges related to technology scale-up. At the end of the 4 presentation about the demo sites, we will take questions from the audience before the closing remarks of our coordinator. And here is the complete list of our speakers of today. Kostis Atsonios from CERT, the Greek Center for Research and Technology, which coordinates our project. Stefano Rebecchi from Bio-Based Europe Pilot Plant, the project partner that leads the activities of the Belgian demo sites. Sergio Iglesias from CIRCE, the technological center based in Zaragoza, coordinating Demo 2 in Spain. Professor Petros Samaras of the International Hellenic University, who leads together with other partners the Greek demo of Fuelphoria, and Marcos Latorre of Perseo Biotechnology, leading Demo 4, also based in Spain. And I will introduce them all in more details before each speaker's presentation. And before we really get started, just a couple of technical remarks from my side. I remind you that this webinar is being recorded, and the recording will be made available on the Fuelphoria website. Attendees are in listening only mode, but we warmly encourage you to write your question in the Q&A section that you see at the bottom of your screen, and also please specify the speaker to whom the question is directed. We will collect them all the questions and we will redirect them in the dedicated time slot to the speakers at the end of the webinar. And I can stop sharing my screen now, and I will invite on stage our first speaker, who is Kostis Atsonios, our coordinator. Welcome, Kostis. And while he's setting up his presentation, I will introduce him. Dr. Konstantinos Atsonios is a Fuelphoria project coordinator and is a PhD mechanical engineer from the Technical University of Athens, and is a research associate at CERT Asperi since 2010. He specializes in the study of advanced energy systems and processes, mainly related to low carbon emissions. He participated in several national and European funded projects, and for example, he was a coordinator also of the Horizon 2020 Biosphere project. He has experience in process modeling and energy system design, performing thermodynamic calculation on various processes, including thermal plants, biorefineries, synthetic fuels production, energy storage concepts, and low carbon technologies and industrial plants. And now I will really stop and give you the floor, Kostis.
Thank you, Piero, for the introduction. Welcome, everyone. I'm going to give a brief overview of the project before the demo leaders explain more details, more technical issues from the very nice findings they have from the project so far. Just to begin, advanced biofuels and renewable fuels with non-biological origin have a major role on the hard-to-abate sectors like transport, the decarbonization of these sectors. Therefore, there are many different ways to produce this kind of renewable fuels. And not only on this slide shows some indicative processes and the ways to produce different kinds of fuels from different advanced feedstock with biological origin, and this slide shows the respective pathways for the production of synthetic green fuels. So there is a lot of effort that has been paid towards the optimization of specific steps on the process level, but there is still a lot of effort that is needed in order to foster this market uptake and to make these technologies into commercialization. And the most important for that is to examine and demonstrate the overall value chains, not only focusing on explicit process steps. And that is the contribution of our project. So Fuelphoria, apart from the demonstration of a robust and efficient technological solution for the production of advanced biofuels and renewable fuels with non-biological origin, the project aims to build a portfolio of sustainable and secure value chains for this production of this kind of fuels, and not focus on a specific part of the process, but from entire value chains from the feedstock supply to the end use of the produced fuels. Moreover, it also aims to promote the exploitation of green fuels, either by the identification of the barriers that should be overcome in value chains, not only in Europe but also in Africa, to provide new policy recommendations at European level, and to develop new business and marketing concepts in Europe and in Africa. As Piero said, this is a European Horizon project funded by the European Union. CERT is the coordinator, and the consortium consists of 26 partners. The main pillars of that project is, of course, the different kind of sustainable features that we are handling, including residues of waste, biogenic CO2 and green hydrogen, a set of competitive state-of-the-art technologies for the conversion of this feedstock into advanced biofuels and synthetic renewable fuels, and the high quality of the end product in order to meet the specifications for use in transport and power sector. And all of this is framed under certain exploitation methodologies that aims to constitute a building block of European actions in achieving improved citizens' perception of on waste as a local resource, and to enable sustainable choices and acceptance of these renewable fuels. The heart of this project is the 4 demos. I'm going to give a very brief overview before the more detailed presentations that will follow. Starting from Demo 1. Demo 1 is located at Belgium, at the wastewater treatment plant owned by Aquafins in Antwerp. This demo aims to the production of microbial oil or triglycerides using as feedstock biogenic CO2 coming from the biogas upgrading unit. and CO2 is converted into lipids into a two-stage biological conversion through fermentation. And depending on the linked value chains, these lipids are upgrading into fuels that can be used as fuel for the transport sector, like aviation, maritime, road transport for heavy truck, and biodiesel as well. Among the different technologies, the most important is the mobile gas fermentation unit. The second demo is located in Spain. In this demo, we also use biogenic CO2, but in that case, it's coming from a winery, from grapes fermentation of Viñas del Vera winery that's located in Somontano in Spain. And together with green hydrogen that's coming from water electrolysis, CO2 is converted into green methane that can be used either as a road transport fuel or as fuel for electricity generation. Here, the key technology is the novel catalytic methanation unit developed by the demo two partners. The third demo is located in Greece. Here, the main aim is to produce biodiesel using algal oil that is harvested and extracted using as a primary feedstock digestate and CO2 that comes from the biogas from a biogas plant that is located in Lagadas in Thessaloniki. They produce algal oil through esterification is converted into biodiesel that can be used either as a transport fuel or as fuel at Atlantic energy systems. And the fourth demo is the second that is also located in Spain. Here is a zero waste approach for the valorization of a great variance of different urban bio-wastes towards the production of bioethanol using an advanced simultaneous alkalification and fermentation process. And the effluents from this process for the production of bioethanol is used either the liquid and solid waste streams is used for the production of biogas and digestate, whereas the CO2 from the fermentation process is hydrogenated towards the production of ethanol and methanol that can be have applications at road transport. Here we have two different demos. The first is located sub-demos. One is located in La Culla next to Valencia and owned by Perseo, and the second at CSIC facilities in Madrid. Here the key technologies is the bioethanol fermenter and the pilot, the catalytic reactor for the synthetic ethanol and methanol production. Now we are in the first months of the third year of the project. I'm happy to say that all the preparatory activities for this pilot has been completed, and all the demos are currently operational, and now they are producing their first results. And the other also key achievement so far is the optimization of these technologies that are enabled in these 4 demos. And since in Fuelphoria there is a portfolio of different competitive technologies, we have biochemical, biological, thermochemical, photobiological conversion technologies. These have been already optimized and tested at the lab scale, and now they are upscaling and start seeing their results at the demo level. I don't like to talk more. You hear more interesting and more information from the demo leaders at the technical presentations that follows. So that's all from my side. Thank you very much.
Thank you very much, Kurtis, for providing the context of our webinar with your introductory presentation of the project. I warmly encourage again the audience to feel free and send all of your questions in the Q&A section down below. And let's now start going more into depth of the overview of the demo operations and the conversion processes across the demo sites. And the first demo leader to take the floor is Stefano Rebecchi, the coordinator of Demo 1 of Bio-based Europe pilot plant. He graduated in chemical and process engineering in 2010 from the University of Bologna in Italy, where he also obtained his PhD in industrial biotechnology in 2018. Before joining Bio-based, he worked as a project engineer at Solaris Biotechnology in Mantova. And he joined Bio-based in 2021. Since then, he has been working as an R&D engineer in gas fermentation, mainly on EU-funded projects. He has experience in the development of and the optimization of bioprocesses and in the design of bioprocess equipment. And the floor is yours, Stefano.
Hello, everyone. Thank you, Piero, for the nice introduction. So I will present the main updates, Demo 1, and the main achievement during the first 2 years of the project. So I will start with an overview of the demo. So this demo is about the production of hydrotreated and esterified TAGs from biogenic CO2 coming from a biogas aquaredding plant via a 2-step fermentation process. The location is Belgium. The feedstock is indeed the CO2 from a biogas aquaredding plant. And the main end products are liquid hydrocarbons for transportation application. So many partners are involved. Among them, we have Aquafin. Aquafin is a wastewater treatment company based in Flanders, Bio-based Europe pilot plant. And then we have CSIC, and then Orlen, Unicre, and Vert. So what about the concept of the demo? So the demo is actually divided into different steps. And I would say that the main categories are indeed the biological processes and catalytic processes. So initially, the biogas is sent to a biogas upgrading plant where biomethane and CO2 are divided. So the first main step of the demo is indeed the gas fermentation process where the biogenic CO2 is converted into acetate. The second biological step is the conversion of the bioacetate into TAGs, so microbial oils. And this is indeed the liquid fermentation. Then the TAGs, so the microbial oils, are converted into paraffin fuels or biodiesel via a catalytic way. The main innovations of the demo are indeed the development of an integrated scheme for the valorisation of the biogenic CO2 into biofuels, and the production of medium and long chain TAGs from biogenic CO2. And obviously there are also there is also the metabolic engineering strategies of the microorganism needed for the production of the TAGs. So we are already at we already passed the second year of a project, and we already have achieved many results for the optimization of the different steps. So I want in this slide, in the next few slides, I will show the main results of the lab scale optimization, starting from the optimization of a gas substrate fermentation process. The objective was to use a wild type anaerobic acetogenic bacteria and to develop a continuous fermentation process at a lab scale, and obviously to maximize the productivity and concentration of acetic acid. The main results, so we were able to ferment continuously for more than 60 days, and we reached a consumption of CO2 higher than 50%. So the process is actually a robust process also for a long period, and we are ready, and actually we are already doing it. I will show it to you later. for the scale-up of the process at 150 liter scale and in real industrial conditions. For the development of the oleaginous strain for TAG production, the partner involved is CSIC CIB, and the main objectives of this task were to use lipid strains like bacteria, rhodococcus, and yeast. So modify genetically those microorganisms in order to improve the production of lipids by increasing the transport of and flux of carbon from acetate to TAGs. CSIC already worked on both the microorganisms, and in particular, they were able to produce 3 Yarrow strain, and they noticed an increased consumption of acetate and production of TAGs. And then they also worked on the genetic modification of the Rhodococcus UST, and particularly they already tested the different acetate concentration in fed batch mode at a small scale. Then we can move to the next step. So actually this is the optimization of the fermentation process for the production of the microbial oils. This task is led by Biobase Europe pilot plant. The main objective was to use an optimized strain coming indeed from the previous step for the production of TAGs. Maximize the titer and productivity by fine-tuning some of the fermentation parameters, and obviously also the optimization of the recovery and purification of the microbial oil from the fermentation broth. We already tested both the microorganisms, Yarrow and Rhodococcus, at a different scale, 4 liter scale and 30 liter scale bioreactor, and we noticed an increased oil productivity and concentration. We also screened different various pretreatment methods and solvents for the recovery of the microbial oil, and we optimized our DSP protocol. So for the TAGs, we are already ready for the scale-up during the next 2 years. We already sent some of the microbial oil to the partner involved in the esterification of the TAGs, and I will not go deeply to this slide. Those are the main results again at lab scale and on a small amount of microbial oil. The partner reached the reaction conversion of approximately 58%. Anyway, I mean, a lot of effort has to be put on the upgrading of the oils. So now I will move to the upscale and challenges that we are facing in this moment for the scale up of the demo at a bigger scale. So in general, I want to give you a quick overview because what we will do and what we are already doing is indeed the scale up of each step of the demo. So first of all, I will start from the scale up of the gas fermentation part. We will scale up it at 150 liter scale, and we will use real biogenic CO2. And then for the production of the microbial oils, we will scale up it at a bigger scale, and the aim is to produce 100 of kilograms of microbial oil. And then obviously also the hydroprocessing and esterifications of the TAGs for the production of biofuels will be scaled up. So I will start from the scale up of a gas fermentation unit. So I want to, this is actually the general concept. So what we already did, and I will show it in the next slide, is to first connect the biogas plant, the upgrading plant, with our mobile gas fermentation unit. The location is so a partner of the project is Aquafin. Aquafin is a wastewater treatment company, and at one of their site they have a biogas plant. So indeed, as I said, the aim is indeed was to connect the gas fermentation plant to the upgrading plant. This happened a couple of months ago, end of September of this year. We faced obviously a lot of challenges, for example, permit from the authorities, construction works, transportation, and integration and commissioning of our system at Aquafin site. As I said, we were able to finish the commissioning last in October this year. And as you can see from this picture, the biogas plant, the upgrading plant, and the mobile gas fermentation unit are now connected. And we are currently running the first test, the tests using the real biogenic CO2 coming from the biogas upgrading plant. I don't have data to show now because really the process are currently ongoing, but we have some promising results. I will move now quickly to the future activities because in the next year we will scale up the microbial oil production. So we will scale up the TAG fermentation. We will go up to 15 cube scale, and we will also scale up the recovery and purification of the DSP. And the last step is indeed the upgrading of the microbial oil for the production of the biofuels. This will be done in two different ways, hydrotreatment and esterifications. Hydrotreatment will be done by our partner Orlen Unicre, and esterification by our Greek partner Verd. There are many challenges also in this case, for example, the selection of the catalyst, and see also if commercial catalysts are suitable for the oil produced in Fuelphoria in this demo. Also for the esterification, there are some challenges and a lot of things obviously to improve, like indeed the conversion. And the process in this case will be scaled up to 250 liter scale. Thank you very much. This is all from my side.
Thank you. Thank you, Stefano, for the first presentation of demo sites. I see there are already questions which I'm taking note of, and we will take at the end in the dedicated Q&A section. And let's move on to the next speaker. Next speaker on stage is Sergio Iglesias from Circe, who will provide an overview of Demo 2. He has a PhD in chemical engineering from the University of the Basque Country with expertise in catalysis, waste valorisation, and hydrogen production. Since 2025, he has been working as an R&D engineer in the industrial process decarbonization team at Circe, and he provides technical support on carbon capture, industrial electrification, and catalytic processes. He's actively involved in European and national innovation projects, conducting techno-economic and market analysis to evaluate project feasibility and potential impact. And he is a co-author of several peer-reviewed scientific publications and presented his work at numerous conferences. I will share his presentation, and we can start. Welcome on stage, Sergio.
Thank you, Piero.
And okay, the floor is yours.
Okay. Now. Thank you, Piero. So my name is Sergio Iglesias from Circe Technological Center, and I will explain the demo 2 of Fuelphoria, which is the production of methane from biogenic CO2 and green hydrogen. Demo 2 is located at Viñas del Vero, Spain, which is a wine factory with more of 1,000 hectares of grape crops. And the demo will target methane production, and the CO2 will be taken from the fermentation process of wine procedure. Hydrogen is currently produced by an on-site electrolyzer with a capacity of 500 liters per hour. And the initial TRL of the project is 5, with a final scope of 7. The aim of Demo 2 is to utilize the captured CO2 from the wine fermentation combined with green hydrogen as feedstock for a methanation process by the Sabatier reaction that you can see on the screen. This is achieved using novel nickel-based catalyst, and the CO2 will be separated, purified from the fermentation gas from the wine, and stored for later use, where it will be converted into methane. The CO2 generated during wine fermentation is carbon neutral, matching the amount absorbed by the vines through the photosynthesis. Here are the project partners involved of Demo 2. Viñas del Vero is the host site, the provider of the CO2 and the green hydrogen feedstock. Circe is responsible for methanation process development and integration. And finally, the University Rovira i Virgili from Tarragona does the development of catalyst and methanation reactor. You can click, Piero. And the demo targets are a hydrogen production of 500 liters per hour, as I said, a methane production in the reactor of 2.2 kilograms per day, and a CO2 utilization of 0.4% of wineries' annual emissions. Okay, so this slide shows the CO2 capture, purification, and storage system installed at Viñas del Vero. And that unit collects the CO2 from the fermentation tanks, compresses it, and purifies it through several filters to remove impurities and also humidity. And the purified gas is then stored in a 80 kilograms CO2 tank at 20 bars, ready for use or transport to the methanation unit. Okay. The captured CO2 in this harvesting period that went from the 20th of August to the 9th of September has been 17 tons. But however, from this, only 800 kilograms are going to be used for potential methanation, since it is the capacity of the tank. The CO2 has a purity of 99.95%, with only CO, hydrocarbons, and ethanol and water as the main impurities, but as you can see, it's very low. And sulfur is below the food grade level, so there is no risk for catalyst poisoning. Okay, so before testing the catalyst in the demonstration reactor, and while the unit was still under construction, we carried out a full series of laboratory scale experiments at the University of Rovira i Virgili. These tests allow us to compare several catalyst formulation under control conditions and to identify also the one offering the best stability, activity, and resistance to deactivation. So we synthesized a nickel-based catalyst, as well as several promoted versions of it, adding 3 different promoters to improve resistance to sintering and coking, named as NIPROM-1, NIPROM-2, and NIPROM-3. I say these names for confidential. All tests were performed at atmospheric pressure with a hydrogen CO2 ratio of 4 and a space velocity of 0.54 mole of CO2 per gram of catalyst per hour. And these conditions are representative of the expected operation at the demo unit. And as you can see, among the promoted catalysts, the NIPROM-3, which is in red in the graph, provided the best CO2 conversion in all temperatures, approaching to equilibrium at 400 degrees and higher. And the NIPROM-1 sample matched the NIPROM-3 only at higher temperatures, while the second one has no significant advantage. We also explore a more complex formulation by adding a small amount of another material as a promoter to the nickel prom 3 catalyst. And the objective was to see if another promoter could further enhance the activity, especially at lower temperatures. The results show a slight improvement, about 300 degrees, but not significant enough to justify the higher cost and complexity of introducing this fourth promoter to the Nipron 3 catalyst. So therefore, this formulation was not selected for the later scale up. So once the best candidate catalyst was identified as the nickel prom 3, long-term tests using real CO2 from the winery fermentation process were done. The test was performed at 300 degrees atmospheric pressure and a hydrogen CO2 ratio of 4 over 1,000 hours of continuous operation, which is equivalent more or less to 41 days on stream. The initial conversion was around 55%, stabilizing at 80% after the first 250 hours, with a very high methane selectivity. What's also interesting is that when the CO2 source was shipped from white wine to red wine fermentation, the catalyst behaved identically, showing robustness to feedstock variations. This confirmed that this catalyst as the final candidate for the Demo 2 methanation reactor. So the method for the catalyst synthesis performed in the lab produces a very fine powder, which is below 1 millimeter. And this size is not suitable for a demo size fixed bed reactor. So two routes to adapt the catalyst for the demo unit were investigated. The first one is impregnation of the nickel, the metal nickel, on promoters onto commercial particles. And the second is cold pressing of the precursor powder, the original powder, to obtain large cylindrical pellets. Here I show the result from the impregnated catalyst. Two samples were prepared, one standard nickel-based formulation and the other one with the promoter we already used. And the impregnated pellets were large, about 1 octave inch. And as expected, some diffusion limitations affected the CO2 conversion. So the promoted version was more active, but still had less conversion than the particle catalyst. So although this method actually works, it's not the optimal solution for the demo reactor. Regarding the cold press pellets of the nickel prom 3 catalyst, they were tested, and they were 3 millimeters per 2.5 millimeter cylinders with good mechanical stress after calcination. And we operate at 360 degrees and a lower space velocity, closer to the conditions expected in the demo reactor. And in this test, the catalyst achieved 82% of conversion, remaining stable after the 90 hours of continuous operation on stream. And the methane selectivity was very high with negligible CO or ethane formation, confirming that the pelletized promoted catalyst is fully suitable for Demo 2. This is the demonstration reactor that we are using for the methanation activities within the Demo 2, located at Viñas del Vero. The methanation unit is designed as a furnace with 2 tubular reactors in series, each coupled to a condensate separator to eliminate the water originated in its reactor by the Sabatier reaction. During the first startup, we carried out the catalyst activation procedure and ensured that the system reached a temperature needed. And at the same time, we performed leak tests across the entire installation to verify the integrity under pressure. And we also performed initial catalytic tests and collected the first conversion data using real CO2 from the winery. So here's an overview of the whole pilot plan, where you can see both reactors into the same furnaces. You can click, Piero. As well as the 2 condensers below, and another click. Okay, that separates the water produced by the Sabatier reaction, as already said, and all the variables in the reactor are controlled from the PLC. Okay, so this slide presents the gas composition analysis performed for the two methanation reactors tested during the first day of the startup, because we don't have more results so far. And using the conditions you see on the screen, with a bit of hydrogen excess with respect to stoichiometry of a molar ratio of 4.57. And in the first reactor, the gas barely contains CO2, and the methane concentration is already quite high with a value of 83%, showing that the methanation reactor is happening almost entirely in the first reactor. In the second reactor, the conversion continues, and all the CO is almost completely consumed, leading to a higher methane content of 89%. And this confirms that the second stage complete the methanation process. So in the following phase of next steps and improvements, we will run long duration tests under industrial conditions to confirm the catalyst stability and the reactor performance. And we will operate with a stoichiometric CO2 hydrogen feed, maintaining temperatures below 500 degrees and working pressures between 5 and 10 bars. We will also work on improving the thermal control to achieve a more uniform temperature profile during continuous operation. And finally, the new data that we are generating will be used to validate and refine the numerical reactor modeling that we were developing during the design phase. And that's all from my part. This is more information about the project, and that's all. Thank you very much.
Thank you, Sergio. And we now go to Greece for demo 3. I see that some more questions are coming in. That's great. And welcome stage Professor Petros Samaras is a doctor of chemical engineer and professor of water technology and environmental protection at the Department of Food Science and Technology of the International Hellenic University in Thessaloniki. His research activities are related to advanced methods of treatment of municipal and industrial wastewaters for the removal of biorefractories and energy recovery from effluents and wastes. He has participated and coordinated around 65 research projects funded by EU and national resources. And currently, he is a team leader in Fuelphoria and a coordinator of another Horizon project, NAMOL. Petros, the floor is yours.
Okay, thank you very much. Good morning. As already said by our coordinator, I'm going to present the demo 3 concept, the demo that is based on a microalgae cultivation for production of biodiesel. So let's see which is the main target of our demo, of our efforts here. Let me say that there are a lot of studies dealing with cultivation of microalgae and extraction of lipids for production of biodiesel. Most of these studies are taking place either using artificial substrate, nutrients, or made at a lab scale. And as you know, at lab scale, everything performs very well. The production of biodiesel might be successful, and any problems that might arise are easily addressed. However, when we are going to a larger scale, we have to, first of all, to consider what will be the cost efficiency of such a system. And in that case, the final product, the biodiesel, has to be compared to commercial products, biodiesel, which is now produced from used recycled cooking oils. And in that case, all the processes that we have to apply should be cost-efficient processes. And we have also to take in mind that energy is another factor that we have to take care. So what we would like to do here, to use wastewater, coming from anaerobic digestion, something that we are going to see later in the next slides, and valorize the nutrients contained in this digestate for cultivation of microalgae. Microalgae then will be used for extraction of lipids and finally production of biodiesel. And this has to be justified in a large scale and having mainly in mind that cost efficiency should be the main target of this process. So there are several tasks here. Of course, the optimization that performed initially at large scale and then transferred to the demo scale, to the full scale plant. The design, the construction, and the operation of the demo, which is of course the main target of our efforts. The development of a control system for optimized operation of our system, the harvesting and the extraction of lipids from biomass, and finally the production of biodiesel from this from the received lipids. So let's see which are the main value chains for our products. Of course, the product will be the same, biodiesel, using the same feedstock and with the same technology providers, the partners which are involved, and we are going to see in the next slide. And the final product can have different applications. Two main applications will be depending on the place which is produced, either for road transportation or for providing power used as an energy source in isolated areas. So now let's see the main process line of what we would like to develop. Here you can see that we start from a biogas plant byproducts, and we use these products in algae ponds, and then different processes are following for post-treatment and production of lipids from, and finally biodiesel. The main action will take place in, I'm trying to, I don't know. Okay, here we are. The main plant here is an anaerobic digestion plant in Lagada, which is a place close to Thessaloniki in Greece. And partners which are involved here, the owner of the biogas unit, Biogas Lagada, this is the owner, and also partners like QLab, International University, Algen, are also involved in this first process, let's say, of our system, where we are going to receive the digestate from anaerobic digestion, and also carbon dioxide as a medium to enhance the cultivation of microalgae. The biogas plant receives livestock production effluents, and depending on the feedstock, the digestate may have different properties, something that we have to consider and something that we are going to discuss later in the next slide. And the main issue here is that digestate management and handling for the owner of the biogas is a really great problem. Since they receive feedstock from different wastewater streams, like dairies or even chicken manure, their digestate might have quite high content of nitrogen. This might reach even to concentrations up to 8 or 9 grams per liter, which is quite high. So now they are considering which would be a good solution, optimal solution for them to handle and to manage this digestate, since they don't have any appropriate methods for disposal or discharge. So this was also our effort. We would like to have an alternative solution for, on one hand, management, environmental friendly management of digestate, and on the other hand, recovery of the nutrients that this digestate may contain. And carbon dioxide is also another issue, and here we would like also to support the carbon footprint efforts, the efforts to reduce the carbon footprint from the biogas plants. And these products, digestates, will be used then for, I don't know why there is this delay. Anyway, we use this digestate as a substrate, as a nutrient feed for inoculation of microalgae. We cannot go directly to the large pond. We have first to prepare a condensed microalgae culture, which then will be transferred to the large scale pond. And sorry, I don't know what's wrong. Yeah, the large scale ponds. And here we have to construct two ponds that will work in series operation and in a two-stage period, cultivation period. In the first stage and in the first pond, we would like to have high growth of biomass. And then in the second stage, in the second pond, we would like to make some kind of a starvation period in order to have a low nitrogen diet of our microalgae in order to turn their metabolism, their assimilation behavior from protein formation to lipids formation. And in that case, we have to receive a lipids-rich biomass. In the next process, algae harvesting will take place using different processing, mainly sedimentation. And yeah, here we are. And then extraction of lipids from microalgae. All these processes will take place by the collaboration of the different partners from Slovenia, Algen, and Greece, BioLab, QLab, the International University, and CERTA ITI, which also support our actions in modeling and simulation of our process. Finally, fractionation of received lipids in order to deliver only the lipids desired for biodiesel production, and the characterization of lipids and biodiesel will take place by Vert, our colleague, our biodiesel producer colleague in Greece again. So we will go quite fast through the activities that took place during this period. First of all, we started to work with the digestate. We would like to have very good knowledge of the properties, the physical chemical properties of digestate, and also what would be the fluctuation of these properties by the time. And in that case, this would provide us a very good concept of what could be the feedstock for our microalgae in the inoculation and also in the large-scale ponds. And in the second action of this part of this period, we had also to go through different species. Yeah, okay. There are also some tables here, but I don't know what's wrong with the presentation. It seems it worked in the test phase, but now it's something's wrong. So you can see here the properties of digestate, and you can see that nitrogen went up to 6 grams per liter sometime, and mostly this nitrogen was ammonia nitrogen, something which is very good for our microalgae cultivation. And then we had to go to find optimum species that can grow into digestate, and the task here was not only to find the optimum species that can afford to survive in digestate. This is a harsh environment, but also we need some species that can provide high lipids content, and of course the conditions that we would like to cultivate in them. The design of a microalgae system. Here is the system: 2 ponds and the smaller inoculant pond, 2 ponds of each one of 500 square meters surface area. You can see here we have to take care of all the piping, connections and everything. And the most interesting and something that we didn't foresee from the beginning was that we have also to construct a greenhouse in order to enclose our ponds and protect our microalgae from intense environmental conditions or even from some external contamination. And then the preparation of biodiesel units, and these take place by VERT, 250 liters biodiesel unit for esterification of lipids from microalgae to biodiesel. And the model system developed by CERT ITI, the technology, the IT group, where what we would like to do here is that we would like to simulate the processes taking place in our microalgae ponds by some kind training our model in the system operation, and finally be able to predict the response of our system under different environmental conditions. And then we went from the lab scale to the large scale to the let's say semi-pilot scale, where we try to transform the results from the lab in the inoculation ponds, and see which are the best species that can be cultivated in digestate, and also the species that can provide lipids with high content, and not all kind of lipids, but only the lipids that are desired for production of biodiesel. And this can be done by combination of species and conditions. In the next phase, we started also the operation of the large-scale ponds. The operation started in October, so we have some first results. We are trying now to establish the best conditions, the optimum conditions for performance. Following the algae harvesting, we are using also a specific protocol, operation protocol, in order to have the settling of microalgae, the easy settling of microalgae in settling tanks, in order to get these concentrating cells, the concentrated biomass, and this biomass then will be used for extraction by different solvents. And this is also a challenging issue here, since hexane is the most often used solvent for lipids extraction from microalgae, but it faces several problems like the recovery of hexane, the cost, or the flammability of the system, and so on. Something that we have to take care if we would like to go on a large-scale process. And what we tried here to develop and use in lipids extraction was different solvents of switching polarity. So we have now an amine that can change the polarity depending on the pH of the solution from hydrophobic to hydrophilic. So when it is in the hydrophobic state, then it can extract the lipids from microalgae, and in the following state, when it turns to hydrophilic, then it can become separated from lipids. So we can recover the solvents and reuse it in a subsequent cycle, while the lipids then can be used for biodiesel production. What we tried to do here was to optimize the conditions for turning the polarity of the system, and using also carbon dioxide in order to reduce the CO2, the pH of the system. And here goes another process that can also contribute to carbon footprint of our system. Although somebody could say that, well, we use carbon dioxide here and then we have to remove it. So it might be something like a process of borrowing. We borrow carbon dioxide for changing the polarity. Several novel issues we have here. First of all, the large-scale production of biodiesel and the cost efficiency and performance of our system. The different methods used for sedimentation and settling of biomass, and here we are going to use also electrocoagulation, flocculation for harvesting, and also the use of switchable solvents for lipids extraction. And here, what we can see in the literature is that there are a huge number of reports on switchable solvents, but all of them are dealing with some kind of some mLs, very small volumes, and this was also something that we had to deal with. And finally, the implementation of some advanced AI methods in order to have this response prediction capacity of our system. The challenges that we have to address, there are several challenges when we are going upscaling, full-scale plants. First of all, when we are dealing with microalgae, we have to take care of potential contamination, or at the same time we have conditions where predators can be grow, and then we might have a collapse of our cultivation. Environmental condition, when we started the large-scale experiments in early October, the weather was quite good and microalgae were very happy to grow in the ponds. But now with the temperature drop down and cloudy weather, it's not so comfortable for them. So we have to also to deal with that. Or even the changes in digestate properties, and this depends upon the feedstock. So the biogas plant doesn't care, or at least what I could say, the biogas plant cares about the production of biogas. And delivery of electricity. So in that case, they use whatever feedstock they can find. And feedstock may change from livestock production to dairies or to food industries, or even to some expired products. And chicken manure. Chicken manure is very low cost feedstock, but it suffers from high nitrogen content. And other feedstock might also include, depending on the season, olive meal wastewater. And so all of us know that phenols might have high inhibitory action to microalgae, and we see phenols in the effluent of the biogas unit. Another thing is the settling of microalgae. Settling, and this also might affect the following processes for extraction, for post-treatment and extraction of lipids, and potential for pre-treatment of biomass, and here we have to target easy extraction and efficient extraction of lipids from the cell content. So we have first to go through a process of cell breakage, cell lysis, and then receive the extract from the cell itself. And the extraction is the most challenging process, I would say, because here we have not only to consider lipids, the desired lipids of high recovery and high purity, but also the recovery of solvent of high purity that can be recycled and will not lose this solvent in the water phase. And the overall process optimization in order to justify the cost performance of our system. So we are going to, in the future, we are going to continue working with a large-scale system, and we are trying to catch the performance indicators that we have set in the application form. And you can see here 2.5 up to 5 tons of algae per year, and from half a ton up to 2 tons of oil per year to produce around 1.7 maximum tons of biodiesel. Of course, we have in our mind to make a replication of our system and in other anaerobic digestion facilities, and we are ambitious or optimistic that we can make this application to 5 different similar cases in order to enlarge, to expand the potential of our process. So that was shortly the demo that we are developing here in Greece, and I see that there are several questions and answers, and I would be happy to address them and to answer. Thank you very much.
Thank you very much, Petros, for your insightful presentation. We have indeed also some questions coming in for you too, and we are collecting them, and there would be time for all speakers to answer the question they have been coming in so far. After our final presentation about the fourth demo of Fuelphoria, and I welcome on stage Marcos Latorre. Dr. Marcos Latorre is the innovation manager at Perseo Biotechnology. He holds a PhD in chemical engineering from the Institute of Chemical Technology from the Polytechnic University of Valencia. And he has over 15 years of experience in developing new materials and processes at laboratory and pilot scales. And he has specialized in advanced characterization for renewable energy systems and biotechnological processes. He has participated in several national and international research and development projects focused on the valorization of waste biomass into value-added products. He's the author of numerous articles in high-impact scientific journals and presented his research at several international conferences. The floor is yours, Marcos.
Hello. Thank you, Piero, for the introduction. So I will describe now the main works done so far in demo 4 of the project. Okay. So the main objective of demo 4 is to demonstrate the production of 2 advanced biofuels, biomethane, bioethanol and biomethane, and 2 RFNBOs, e-ethanol and e-methanol, from urban biowaste. Okay, so in this demo, the urban biowaste will be submitted to an SSF process for the production of advanced bioethanol, and in this process, 2 byproducts are generated: vinasse, which will be valorized by anaerobic digestion to produce biomethane, and CO2 generated in the alcoholic fermentation. And this CO2 will be catalytically hydrogenated to produce the e-fuels. 3 partners participate in demo 4. SAP is the supplier of the urban biowaste. Perseo deals with the biotechnological valorization of the waste into ethanol and biogas, and FESIC is involved in the catalytic conversion of CO2. So here we can see the KPIs of the demo. We will treat more than 50 tons of urban biowaste during the project. We have a target of 130 liters of ethanol per ton of biowaste and 700 cubic meters of biogas per ton of volatile solids in the anaerobic digestion, with 65% of methane content, and we will treat 75 kilograms of biogenic CO2 to be converted into advanced liquid biofuels, and the conversion target is 10% for CO2 into ethanol per reactor pass, and 50% by recirculating, and 20% conversion of CO2 into methanol, and with the yield of higher than 90% by recirculation. So demo 4 will practically showcase value chain 8 and 9 of the project, where the viability of the production of advanced ethanol, e-ethanol and e-methanol production from urban biowaste will be demonstrated, and these renewable fuels will be validated for road and maritime transport. So SAP, which is the supplier of the urban biowaste, is a large environmental Spanish company which offers 3 main services: collection and management of solid urban waste, wastewater treatment and urban services, and maintenance of cities. So in these processes, three main biowastes are generated and which were evaluated as feedstocks for demo 4. And this we can see here in the pictures. So different industrial plants from Valencia region will supply the urban waste, and this waste will be composed of a mix of separately collected and non-separately collected municipal biowaste, and also sewage sludge from wastewater treatment plants. And and also SAP got the permissions needed to supply all these wastes for the project, and also different batches of from different periods were chemically characterized to know the composition and potential. So currently in Valencia city, around 60% of municipal biowaste comes from a separate collection and 40% from a non-separate collection. And by mixing these two biowastes, the composition of the feedstock that will be used in the motors will be the one indicated in the table on the left, with around 30% of carbohydrates and around 10% of fats and proteins. Regarding the sewage sludge, it contained around 2% of solids, and no inhibitors were observed for the fermentation, so it could be used as a substitute for the water in the ethanol production process. So then regarding the preparatory activities of the meteorological demo plant from Perseo, in the bioethanol unit, the enzymatic hydrolysis step was optimized at lab scale. The fermenting microalgae was selected with a high sugar conversion yield. The sewage sludge did not generate any emissions, so it can replace the necessary water in the process, and the potential of ethanol reached the target that we had for the demo. And the pilot plant was adapted to the project needs, and 10 cubic meters per month will be used, which means using around 4 tons of solid waste batch and 4 cubic meters of sludge, and also we install a new 2 cubic meters digester downstream in the plant. Yeah, so the first demo trial consisted of using organic urban waste from non-separate origin mixed with water, and as we can see in the plot, the plant trial and the lab control performed in a similar manner with a good yield of SSF. Here, the main disadvantage of using this biowaste from a non-separate source is that it contains relatively high inert materials and low content of carbohydrates, so it decreases the potential of ethanol per ton of feedstock. So in the next trials, we will use richer streams based on separately collected biowaste as raw materials. We also tried a sample of leachate, which is a waste from municipal solid waste treatment plants. We use it at larger scale to substitute water, but in this case, it inhibited the fermentation due probably to the presence of different organic acids that are known to be inhibitors for this bioconversion. So in the biogas unit, we completed the lab test to evaluate the fermentation vinasse and its biomethane potential, and the fresh and the fermented material were characterized, and as well as the anaerobic intercooling. And we obtained typical values for this kind of substrates, but with a 10% higher production of biomethane in the case of vinasse. Perseo designed and assembled a new 2 cubic meters digesters in the demo plant using different suppliers, and the digester was installed within with an ATEX zone with all the required sensors and control system. And the pilot digester was commissioned recently with using 2 cubic meters of anaerobic sludge from our wastewater treatment plants from SAP, and it will be fed with the vinasse from the ethanol trials, and the starting organic loading rate will be increased gradually, and here and we will see the evolution of the production of biogas and digestate, and here below we can see the parameters that will be monitored continuously during the anaerobic digestion process. So now we move to the catalytic part of the demo with the CO2 hydrogenation into e-methanol. The work at laboratory scale began with tests for methanol synthesis using a commercial copper-based catalyst, and tests were made in a fixed bed reactor at 240 degrees and 50 bar, starting from CO2 and hydrogen. And a CO2 conversion of 25% was obtained and remained stable even after 140 hours. And methanol activity was up to 43%, and the other main product was carbon monoxide. And following these results, a copper-based catalyst was developed, leading to a recent publication by CSIC in Catalysis today. And in this work, the influence of different magnesium loadings was tested. And magnesium is a promoter known to increase the basic character of the catalyst, improving its interaction with CO2. And the effects of the promoter were observed both in the structural properties and in the also in the catalytic activity. So it was observed that magnesium improved the structural properties of the catalyst active phase, increasing its dispersion, the number of active sites where the reaction occurs, and also the surface area. And all these properties are beneficial for enhancing the interaction between the catalyst and the CO2. However, the best catalytic activity was observed for the catalyst with the intermediate promoter concentration, using the same setup for the lab scale catalytic test. A stable CO2 conversion of 20% was achieved even after 120 hours of reaction, along with methanol selectivity of up to 50%. So the catalytic test conducted at laboratory scale with have the aim of being scaled up to a pilot plant, specifically designed for CO2 conversion with green hydrogen using heterogeneous catalysts. And the goal is to achieve 20% CO2 conversion into methanol per reactor pass and up to 90% by recirculation. And following this idea, the construction of the pilot plant was recently completed, and it reached CSIC facilities. The plant was designed to fit into a container, making it easier to move, and is expected to be commissioned in the coming months. So, as a conclusions, in this period of the project, per se optimized lab scale depletion of 2G bioethanol from organic urban waste, and the first demo trial was performed. A pilot digester were commissioned and will operate in continuous for the next months using the vinasse as input. A catalyst for methanol production from CO2 hydrogenation was developed and is stable over time and with optimal reaction conditions, and it is awaiting for pilot scale testing. and also the pilot plan was really completed and has been recently sent to the ICP facilities of CSIC. So for the next month, our plan is to complete the optimization for the advanced bioethanol production from urban biowaste at demo scale, also the biogas production, and carry out novel synthesis of a series of catalysts for the conversion of CO2 to ethanol. Also to test the real CO2 stream from the process fermenter, taking into account possible impurities, and operate the catalytic pilot plant within the facilities of CSIC to optimize both e-fuels production from CO2 hydrogenation. And that's all. That's a summary of the work done in Demo 4 in this period. Thank you for your attention, and I'll be happy to answer any question you may have. Thanks.
Thank you, Marcos. I would like to thank all of the presenters, the demo leaders. I think that also the audience find it quite interesting, all these aspects that were addressed by you. Now we are moving to the Q&A session, to question and answer. So far, we can see some questions already at the chat. There is still time to make any question to all the demo leaders, and especially for Marcos, maybe for that. And start to begin with the questions that are related to demo 1. There's questions related to the paraffinic fuels, in which sectors exactly are paraffinic fuels planned? Are there to be mixed with fossil marine fuels, for example, and offer as blends like B30? I replied by text that the paraffinic fuels that are produced at demo 1 is hydrotreated microbial oil and planned for transport sector like aviation, maritime, low and road, depending on the different from the fractions that are produced and extract after the hydrogenation, the distillation and fractionation process. And we are going to perform certain tests, but the main aim is to maximize the blending ratio. Two additional questions to Stefano. The first is in which aspect the first facility process is different from LanzaTech LanzaJet route, which is at industrial scale by now. Marcos would like to answer that. Sorry, Marcos, Stefano, would you like to answer on that?
Yeah, actually the main difference is the final product of the gas fermentation process. So LanzaTech produces ethanol as a final product at industrial scale, as far as we know. And in our process, we produce, the final product is acetic acid.
Is there any specific difference in the strains that you use?
Yes, many difference obviously also about that in terms of process. We are actually using a wild type microorganism, so not genetically modified microorganism. And as far as we know, LanzaTech is using a genetically modified strain. If I remember well, it is a Clostridium. I don't know exactly strain, but it should be a Clostridium. So that's also indeed another difference.
Okay, and one more question related to the hydrogen production by electrolysis. Is planned to be integrated?
Yeah, it is integrated. So actually this is part of the demo. So indeed, hydrogen is supplied by an electrolyzer.
Okay, thank you, Stefano. Okay, regarding demo 2, there are two questions in the chat. The first has to do about the pellets production, and when producing pellets from the catalyst powder, have you used any binders to tune pellet properties? This questions has been answered by Francesco Medina from Rovia Virgil University, that they don't have used any binders, only pressure for the pellets production. I don't know if Sergio would like to add more on that.
No, nothing on that.
Okay, and a second question, Sergio, for you is: did you experience any challenge during the initial operation of the methanation unit, considering how exothermic the reaction is?
Okay, yeah, I would say that the main challenge during the commission and the first starting up of the methanation reactor was achieving a more or less stable temperature along the reactor. Because, as the question says, the methanation is very exothermic, and maintain a temperature profile during the reactor wall, or let's say length, is important to avoid the formation of the hot spots, and also because it can lead to catalyst sintering and then the activation. So we were seeing temperatures at the inlet about 500 degrees of the first reactor, that where is the majority of the conversion is happening there. So we believe that the reaction was happening too fast, and even if we decrease the temperature of the furnace, that the temperature inside the reactor didn't decrease so much. So we were trying different approaches to resolve that, because we believe that the stack effect in the furnace that makes the upper region slightly hotter, because the hot air goes that way. And to address this, we were evaluating some improvements, that feeding the gas from another part, maybe the lower part or something like this, and also to try to adjust the catalyst dilution, because we believe that maybe at the inlet the dilution is not so or enough high to avoid this hot spot problem.
Okay. Thank you, Sergio. One more question from my side. Since CO2 methanation is not a new process, most of us it's already known. However, do you think there is still challenges at catalyst development or at the reactor design before the technology moves forward to bigger scales? And what makes the developed catalyst in Fuelphoria special, according to your opinion?
Okay, I will respond more or less in the same terms I already said. I believe there are still some challenges to be addressed. The reaction is very exothermic, so there are different approaches to do that with respect to the reactor design. For instance, I saw some studies that they talk about some polytropic reactors that consist in a multi-feed inlet, to try to avoid that the reaction happens so fast and generate a hot spot. And we are using a different approach, but more or less let's say the principle is more or less the same. It's to try to split the conversion in two stages. So that's why we were using two reactors in series, to try to avoid that the whole reaction is happening in the same step. And regarding the catalyst, as you said, I believe it's very important to avoid the sintering, because the hotspot can promote the sintering in the reaction. But the catalyst we were testing, made by the colleagues of the University of Rovira Virgili, show that very good stability and very high activity. And it maintains the performance after the pelletization. So we believe that this catalyst is going to be stable very, very long, and it will work a lot of hours. And it's not going to be affected so much by this exothermic reaction.
Thank you, Sergio. Okay, two questions for Petros related to demo 3. Is the choice of biodiesel as target product related to low cost of transterifications versus other upgrading routes, or to feedstock like methanol versus hydrogen sustainability and availability, or are there instead other specific reasons? These questions relate to why we focus on targeting on producing biodiesel and not something else.
Yeah, well, I guess that there's another following question, which is more or less in the same line. When we started to talk about that project, we had in mind to develop a solution for the biogas plant owner. And the problem was that they had the digestate with nitrogen around 5 grams per liter, and they didn't know what to do. So the naturally microalgae as photosynthetic organisms grown in nutrients could provide a very good solution for that. But then we had to deal with the biomass, what to do with that. So biodiesel was let's say something which was known from lab scale, and that could also work very good at large scale. And we started with biodiesel. We had already one problem, which was the digestate itself. The second problem, the microalgae growth. The next problem, the extraction. So biodiesel, was one solution quite easy, common, that could provide us a product, an easily produced final compounds that could also give us the solution to handle the digestate in a quite good valorizing way. We could also include, as I saw in the next question, SAF. That could be a very good option. But then we could go to, and this could also provide a higher added value product. And then we shouldn't take care so much about the process and the cost efficiency. But we would like to go on a safe way. We knew at lab scale that this works. And we could deal with management of digestate, growth of microalgae, extraction, and delivery of biodiesel in a safe way. But finally, it seems that it's not the same way so far as we understand, and we have to justify that. So shortly, the question is that we used biodiesel because this was a product that we could reach addressing all the other issues, but we could also see some other options. This could be the target of a next project.
Okay, thank you. And one more question about the CO2 feeding. Do you bubble it through or feed it as a bicarbonate?
Yeah, that's another discussion. We are going to add it as bubbles, but we have first to go through a treatment to remove any traces of hydrogen sulfide and so on before adding that. Carbonates, there are a lot of carbonates and alkalinity in our effluent, so we don't have any option for that.
Okay, thank you, Petros. And if I have a few minutes for one more questions from Demo 4, since I don't see any questions related from the audience from Demo 4, I have one question to Marcos about the bioethanol production process that is presented in this demo, that has a very strong advantage in terms of feedstock flexibility. And I would like to ask, what are the main compounds that you are seeking at the various feedstock types and enhance the process performance bioethanol yield and substrate for biogas? What are the compounds that you are seeking at the feedstock to select in order to select the best for the process?
Yeah, I mean, for the production of bioethanol, the best, the better feedstocks are the one rich in carbohydrates, okay, because at the end the carbohydrates are the ones that you convert into sugars and then to ethanol. And also it's important to have materials with lower humidity as possible, because for things like logistics and transport, the less moisture you have, the better. And also to avoid, which is something difficult, to avoid a high content of inert materials, which are the non-biodegradable, which are they are non-biodegradable, and they can decrease the efficiency of the process, and also you can have problems in the facilities. And for the biogas production after the process, as it has been reduced these materials, and you increase the content of fats and lipids. So we see that this process is enhanced when you use the vinasse versus the fresh material. So these are the main considerations regarding the feedstock.
Thank you very much, Marcos. I think that the Q&A session ends. Thank you all for your attention and participation in this webinar. From our end, we would like also to ask you to stay tuned and follow the progress and updates for project, following and check out our website. Follow us and at LinkedIn, and also if possible for any further questions, Piero and me are at your disposal. So Pierre would like to have a closure word.
Yes, thank you very much, Kostis, and thank you all speakers for your presentations, and of course, thank you very much also to all the attendees for their questions and your participation in this online event. As Kostis mentioned, you can further address us any questions, and I put both our website and our LinkedIn page in the chat, as well as our email addresses that you have seen also in a previous presentation. We're definitely looking forward to seeing you again for the next webinars, and also in-person events which are already organizing, and that will take place starting from the first half of next year. So again, I warmly encourage you to stay updated with the Fuelphoria news, and thanks again for your participation, and I wish you a great rest of the day.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you all.